Hey everybody, in this video we want to solve problem 52 on daily LeetCode challenge n queens 2. So in this problem, we are supposed to place n queens in an n by n chessboard table such that no two queens attack each other. So this problem is a more general version of an 8 queen problem, but such that in this problem n could be variable. So the size of the chessboard could be different. So let's first talk about some facts. So we know that whenever we place a coin in the table in a board, we can no longer place any other coin in the same row or in the same column of the coin that we just placed on the board. So if we iterate from the rows, so from row 0 and then go to row 1, 2, and 3 in this case, we know that if we find a place for a coin on row 0, then we should go to find another one on row 1. And since we are supposed to place n queens in an n by n, and we can not put two queens on the same row, that means on each row we should be able to find a place to put our queen and then go to the next row. So this is how we are gonna use backtracking to solve this problem, and we iterate rows by rows, so starting from 0 to n minus 1, and then on each row, whenever we find a place that there is no other queens already threatening or attacking that place, we try that or place that, and then we go to the next row until eventually we eventually fill all n queens in the table and consider that as a valid result. So for example, whenever we put a coin here, we remove all of these rows, columns, and then all these four directions that this specific coin attacks, and then pass it to the next row using backtracking to find or try other places, and eventually we are moving into this tree of children's and find all possible answers. So before implementing that backtrack, I want to implement a board class so that we use for this problem. So first of all, for initializing, these are the boards that we place a coin on and then pass it to the backtrack for the next iteration or for next rows that we are eventually trying to see if there are valid solutions. But here we use it so that we copy the whole table and pass it to the next one, so that we don't change the, because whenever we pass arrays in Python, these are being passed by references, and then the objects themselves are passed to the next one, but whenever we try this one, we want to also try the next one as well without changing the previous iterations. So for size n, and then so we know that the board itself, the board equals, let's availability, this is the board, we just consider two states, whether that place is available or not, so it's a true or false. So initially all of them are true, or I can for easily say true times n here for in range n. Sometimes without initializing the board itself, we want to copy from other board. So if other board is none, we create a new board. Otherwise, we just copy the other board. So self.board equal C for C in row, for row in other board. So this is the 2D array of other board, and then we are just copy that and store it here. Also, we can say self.n equals n, so that to keep track of that. Other useful functions is get availables, or for each row we get all available options. So for example, if we place it on the first row, so this queen will remove all of these cells that threatening, and then when we move to the first row, or starting from 0 to here, as you can see, all of these cells are already taken, and get available for row 1 should only return one option. So we can define this function, get availables, and then row number, and then we just return j for this is the columns. So for c, for c event self.n, if self.board of row and c. So if this is true for just a specific row, we are iterating through n. We could store it all available columns as well, but since the number of the maximum value for n is 9 in this problem, so we can on each availability test we just iterate through at maximum 9 iterations. So this is not that much, so we can use that. And if that cell is true, we are creating a list of all available options for that specific row. The other useful function for the board is to place a queen in a cell. Whenever we place it, we should update the board such that removing all or changing the state of the all threatening cells from true to false, so that in the next iterations no one can place a queen in those places. So if I define a place in the row and column, then first of all we should remove all cells from the current row. So self.board I4 or we can say self.board row equals, or let me change it. So for I in range n, or self.n, first of all we remove everything from the cell and column. Self.board row and I equals false, as well as I and column. So what we just did is just moved horizontally and vertically and removed all options because we are placing that row and column value. And with 4 directions for di and dj in, what are the 4 directions available? So whenever we place a queen, so we move diagonally in a diagonal way, southeast, northeast, northwest, northeast, and southeast. So these are the 4 directions: -1, 1, 1 and 1, 1 and -1, and -1 and -1. So we are starting from this, and these are the directions. And what are the starting point or column? And so x and y equal to row and column, while these are valued. So while x equals self.n and 0 self.n, self.board of x and y equals false, and then x and y equals x plus di and y plus dj. So we just move in 4 diagonal directions and then remove them. What we could also do with replacing this and add these other 4 directions as 1 and 0 and so on, but we already handled the column and row, so this is okay. So we just placed here, and that's it for now. So it should be fine. Moving to implement the backtrack itself. So def backtrack. For each iteration, this is a recursive function. For each one, we are given a board and the row number. So remember, we are starting from 0 and then eventually going to 1, to n and minus 1. So as soon as we see that row is greater than or equal to n, so we should return 1, because that means for the very last iterations, starting from 0, 1 to n minus 1, as soon as we see this is the end, that means all of the previous iterations are handled successfully, because if there were no available options for some row before n, that means no solution were found and we just return 0. Otherwise, as soon as we get to the nth row, that means all of the n queens are already placed successfully, and this is a valid answer, and we are returning 1. Otherwise, this is the row number. So for C, this is the column number in board dot get availables of that row number. A new board is a board we are just copying from the previous board. So this is the n and the board. We are creating a new board from the given board, so that we are just making a copy of that board, so that we don't change it. This board that is stores all information from the previous previous iterations, and then new board dot place. This is the row number. The row number is the current row, and C. Or for more readability, I can say for column, and then change it to column, and then valid answers from the current state initially is 0, and then valid answers plus equal backtrack. We are placing that on all available options for the current row. We are placing and then running the backtrack on the new board. And row plus 1. We are moving to the next row. And this backtrack should either return a couple of all possible answers or 0. So we are adding the answers, storing the current state in this valid answers. And then after that, just returning valid answers. And initially, we are restarting our backtrack from a brand new board, because if other board is not given, so it is just initializing a new table with all true values. So we just return, just put 1, and the other one by default is none, and creating a brand new table from row 0. And just like that, let me try. So invalid syntax. Let's see. Oh, I forgot to put an if. Okay, so let's try other test cases. The edge is 1, and the rightmost edge is 9. Okay, so it should be fine. Let me submit that. Okay, we handled to run this problem faster than the problem that repeats almost a couple of months ago in 2021, but this time we handled successfully. Let me see, what did I do last time? Quite the same idea, but instead of using a class, I used functions, but here with the help of implementing all useful functions or needed function in this class, so we make our backtrack function more readable and easier to implement. So that was everything for today's problem. Hope you enjoyed it.